Hello guys, welcome back to Tux Writers. In this video we want to talk about compile process inside Linux using GNU Compiler collection, as well as the build systems like GNU Make and CMake. I think it will be an exciting episode, so let's jump into it. So let's have a look at the compile process, how we compile programs inside Linux. For that, I will compile a very simple C++ program, but from next videos we will start to compile really huge programs, huge libraries. But the concept is more or less the same, because I want to also show you how I can use more advanced tools to compile this simple program. And those advanced tools will be used to compile bigger programs and install indeed bigger, let's say, libraries into the system. So for the demonstration for purposes, I will let's call it test. Again, I'm happy with this name. So I create a test folder on desktop. I open that with an editor, and also I open it inside my terminal. Okay, cool. What I want to do is I want to create a C++ program here, that does nothing but printing something on the screen. So I say include IO stream, and I say using namespace std. Why I type like this? I don't know. And then int main return 0 means success of execution, and I want to say hello world. So a very simple, sorry for my typos, I don't know why this happens. Okay, yeah, a very simple C++ program. Let's see how we can compile this inside Linux. For that, I will use GNU Compiler collection, GCC, or sometimes it is also called GNU C Compiler. In this case, it is indeed GNU C Compiler because this is the C compiler of the collection. So what I can do is I say GCC and then my source file, and that's it. But because this is a C++ program, I have to use GCC C++ compiler, and as a result I call this on my C++ source files, and then if I list the content of the directory, I can see that, yeah, I have an executable here. So this is indeed the output of the compiler when it compiles my program to this very simple C++ indeed application. And if I run it, I have told you before that if you want to run it, you have to put current directory / and the name of the executable. So that's pretty cool. This is the simplest form of programming, the most minimalistic way. But why the name is out? Let me remove out, and I can use the switch O to name it whatever I like. So when I say main, you can see that now the name of the program is called in the name. So I can call it, I can run it like this. Sorry, it's I mean main. So when I name it main, it will be a main, the file main. It's very similar to exe files in Windows. Okay, let's make it a bit complicated because I want to show you this is a very simple form. Let's see what if we have even more files into the system. Just imagine that we have a helpers CPP and helpers.h, and in helpers CPP I want to add something like an add operations. I want to say int a, int b, and this does nothing but returning the the sum of A and B. And I need a header file. This is indeed a C++ concept that, I want the other, let's say, source files know what I have inside this helper CPP. So what I have to do here is I have to helpers.h, and then I can have, for example, I say cout add 3 and 4. Yeah, cool. Let's see if I can compile it. Now, if I want to compile this, I have to provide it with both source files, like say CPP and then the helpers.cpp, the CPP file, the header is not something that I want to pass to the compiler, and then I will say name it main. I run it without any error, and yeah, you can see that I have main here, and when I run it, yeah, this is the way that now my program had become a bit more complicated. So yeah, that's still fine. Let me also show you some other workarounds to compile programs. So I have 3 files. I can also compile them one by one. This is indeed a way that when you compile a bigger program, you see that the build system usually compiles it like this, that it compiles every single file in the source directory and then combine them all together using a tool called linker. I don't want to go to the details of that process, but yeah, this is how it works. In order to ask GCC to compile only the files, each file separately, I can use the switch C. When I say GCC, G++C, you can see that it generates an intermediate object for me. So I have to do the same with my, let's say, helpers CPP. And then I have 2 O files. And in the end, I have to say main.o and helpers.o with the output called main. That was easy, isn't it? So I can easily now call main, and that's the same output. This is indeed the way that build systems work. But what is a build system? In bigger programs, if they have, for example, imagine that instead of 2 source files, you have like 100, 200 source files, and you want to compile them. Then you cannot go, for example, one by one and then execute a compiler on them, because they have also different dependencies, and then it becomes complicated very soon. So in order to avoid that, on top of the compilers, there are also some tools developed, for several decades called build systems. The most famous build system in Linux called Make, GNU Make, which is indeed which accepts a file called Makefile and tries to execute the file in a way that results to a compiled program. But what a Makefile describes, indeed, the content of Makefile describes the dependency between various source files and the way that the final output should be built. Let's create a simple Makefile for our program. Let me remove all my intermediate files and also the main. So here I have nothing but the essential source files. You can find in the description two links to two good web pages that I want to use in this video. One is the one I found in I think National University of Singapore. I'm not sure, but yeah, this is a very good guide to make GCC and Make and all compiling, linking, and building C++ programs. What is really nice here is a simple Makefile that they have. You can go through this tutorial This is very similar to what I did here, but I think the examples are for C programming language, but there is no difference. What I want to have from this indeed web page was this simple makefile. So let's copy it here and then I will describe it. So before that, I have to create a makefile like this, and then inside our makefile it should be like this. You have different these are different indeed targets, all and clean, and these are dependencies. Indeed, these are also some targets, but the dependencies are listed here, and then it says for compiling this dependency, follow this. So let me describe it a bit simpler. The target all means that in the end, we want to have the program, let's say main here. Sorry. For building the program main, it's developed for Windows. For program main, what we need is indeed main.o, and as you saw, helpers.o. So these are indeed two dependencies to the main, which was indeed a dependency of build everything. And in order to create this main, I will come back to this, but for creating this main.o, which was indeed one of those intermediate files, what should be run is G++ compile only main.cpp. So as you can see, in order to, you can see the similarity to the way that I compiled each of these source files separately. In order to build main.o, I need main.cpp, which is indeed can be achieved, can be built using this command G++ compile only main cpp, and I need a very similar thing for for helpers. This makefile are very sensitive to spaces, so it should be exactly 4 spaces helpers. So G++ helpers.cpp, and then this object depends on this. And then after compiling these two, it comes here, and for building the main, the final main, it should execute G++ main. I want an application be called main, and then main.o and helpers.o. So this is the exact equivalence of the steps that I took to compile the program by compiling each source file one by one. And the big advantage of this is taking advantage of taking care of dependencies, but at the same time taking care of the way that you have to update the final output. If you change this helper cpp file, then Make is smart enough to discover that this source file is changed, and as a result the output is already outdated, so it should compile this helpers.o only and then come back to this and run this one. So just imagine that how helpful this will be in compiling a very big program. But let's see if it works. In order to take advantage of this GNU Make, you have to run this make command in a directory containing the makefile. So the makefile is here, and when I type make, it goes through this makefile and tries to execute that. Let's see if it works. Wow, very nice in a first try. Yeah, usually that doesn't happen in programming, but yeah, it worked. And let's see what we have here. We have main. That's super nice. I run the main, and you see that we have here 7, the program that we had. But let's go back to the source files and change, for example, I change it to 3 and 8. Now this helper CPP is not outdated. It's as the same as the previous version, but I have updated the main CPP. So I had also this clean command. I don't want to use that. Let's see what happens if I say make. It, as I told you, it detects that the only source file that is changed is indeed main and not helpers. You see that the helpers is not around here. So it updates the this main.o and then updates the executable for me. Hello world and 11, and I had also clean, which was indeed here. Let me show you clean. Oh, it's incorrect. It should be main.o, helpers.o, and main. Cool. So if I say make clean, you see that it cleans the output of the build process. Okay, that's it. But let's go to the next step. The next step is, imagine that you are working on a big project, and on big projects, even creating a makefile becomes complicated very soon. So we need other tools that can generate this makefile for us. So we can go for tools like CMake. CMake is indeed a build system generator. So it generates this makefiles for us by interpreting a script file that is indeed a source. It is indeed an input to CMake program, and then we can easily take advantage of that to build bigger programs. You will see in next videos that most of the programs that we're going to install are released with this CMake install process. In order to take advantage of CMake, we need this is the second link. You will find it in the description, which is indeed a URL to a link to CMake, a very simple CMake tutorial. I don't want to go through this. What is really important for me is, just this simple CMake script. That's enough. But what CMake needs, indeed, is a file called. Why I always type this incorrectly? CMake lists.txt, I think. I'm not sure. Yeah, CMake lists.txt. Yeah, that's correct. CMake lists.txt. And then the content can be, it can be a very complex script. As you can see, it's a sort of program language. You need to learn. CMake is indeed a language, a scripting language to generate makefiles. But I want to work with that in its most straightforward way. So it said the minimal version of CMake required is 3.1. Let me check which version of CMake I have. I have 3.16. That's good. So if you don't have CMake, you can easily install that using apt. So you have to say sudo apt install CMake. And then the project is tutorial. I can say that I want to use main. The project name is main, and for building main, I say that the main is dependent on a main.cpp and helpers.cpp. And I think, yeah, that's it. That's all we want, and CMake will take care of the rest. So we have CMake list.txt here. One of the common approaches in using CMake, because it generates some intermediate files, is creating a build folder. We go to the build folder, and here we call CMake, but CMake list file, CMake lists.txt is in the parent directory, so we say CMake parent directory. And then it starts to detect things. You see that it detects the the compiler, the C compiler on a system. It can be any compiler. In this case, this is GCC, and it tries to because here I didn't say that any special library or any special compiler feature is required. It didn't it didn't go through that, but yeah, this is the way that it works. So you can see that we have lots of things here in this folder and also here, but we have also a Makefile. This is indeed pretty cool because yeah, the CMake has generated a Makefile for us. So as you see, CMake didn't compile the program. It generated the Makefile, and then by taking advantage of Make or any other build, let's say build system, we can compile the program. I type make and oops, sorry, it's ls, and yeah, sabracadabra, we have main here, and let's run it. Wow. So this is indeed the way that CMake works, and as you saw, the output of the build is different from the GNU Make, because CMake adds some custom output, custom print statements, and custom, directives. So the output would be a bit different. But yeah, this is indeed how CMake works. This is indeed very, very useful for building big projects. And as you saw, by taking advantage of these build systems and also this build system generator, you can decrease the dependency of programs to the platform that is in which they are going to run. So if you develop a program, like imagine that you develop your own finite element solver or scientific computing library, you can take advantage of these tools to release it to users. And it doesn't matter what kind of system they use. These tools take care of that for you. They detect the compiler installed, and they compile the programs optimized and tuned for the system that they are going to run. Because by using this, it's not important anymore what kind of configuration the user has on his or her system. And that's why this is indeed the preferred way of installing programs in Linux systems, especially for scientific or data science applications. And from the next videos, I will show you how to use these techniques to build programs, to build big programs, really, huge libraries. But yeah, the core concept is nothing more than this. I hope, yeah, this video was useful for you. Make sure to reproduce this workflow, and yeah, just enjoy it, and see you in next videos. Bye.